Okay, welcome you all. Today we are going to continue with Norton's theorem and max power transform theorem. Last class we saw Thevenin theorem. So these are additional two theorems which are as important in electrical sciences. So what are the applications of Norton's theorem? In last class we saw how a complex circuit could be represented as a single voltage source and a series in resistance by using Thevenin's theorem. Norton's theorem does also a similar job. Only thing is that we are going to represent a complex network by a current source and a parallel resistance instead of a series instead of a voltage source and a series resistance. Norton's theorem is going to we are going to represent a complex network by a simple current source and a resistance in parallel. Okay, so it reduces a network to simple current source and parallel. That's what it says. Okay, now the definition goes like this: a linear two-terminal circuit can be replaced with an equivalent circuit consisting of a current source IN in parallel with a resistance RN, where IN is the short circuit current through the terminals. So you have an output terminal. So for Thevenin equivalent, we were measuring the open circuit voltage there. In this case, we have to measure the short circuit current. That is, we need to remove the load resistance and short both those two output terminals and measure what is the current flowing into that short circuit. Short circuit wire which we have placed there. Okay, so that is going to be called as IN. So that is IN, and RN is exactly same as that of Thevenin, wherein it is the resistance seen from into the circuit from those ports after removing the independent sources. Okay, so this is how we derive the values of I and R. Now what are the steps to determine the Norton's equivalent resistance RN and current IN? RN is exactly the same way as that of RTH, whereas to find Norton current IN, we determine the short circuit current flowing at that output terminal. This short circuit current in the Norton equivalent will be known as IN. Okay, so we'll see an example, so things will be absolutely clear. Okay, so before we take on an example, there is we need to understand there is a close relation between Norton's and Thevenin's theorem. If there is a circuit, we can represent it by Thevenin's equivalent, which is a voltage in series with an Thevenin voltage in series with a Thevenin resistance. Same circuit can again be represented as an alternatively, this is an alternate option which is available to us, wherein I can represent it by an current source in parallel with an Norton resistance. Now in both the cases the resistance will remain same if I compute the resistance, because the resistance is by removing the sources of power and looking into the circuit from the output nodes, right? So the procedure is same, so these values remain same, and whatever we get the value of IN, okay, it will be same as that of VTH divided by RTH. Okay, so this can be used for transforming the, if you have an Thevenin circuit, you can represent it by an Norton circuit like this by using this formula: RN is equal to RTH, IN is equal to VTH by RTH. Okay, so this is an useful transformation where we can transform a Thevenin circuit into Norton and vice versa. So we will take an example how to find out the Norton equivalent of an circuit. So here it says find the Norton equivalent circuit to the left of the terminals AB. Okay, and find the current in the 50 ohm resistor using the equivalent circuit. Okay, that means we need to consider this 50 ohm as an load resistance. Okay, so first to find out the short circuit current, what we need to do is we need to remove that 50 ohm and put an short circuit there, so which will be known as ISC, and finally this is going to be the Norton current source. Okay, so we have removed that 50 ohm. and across the terminal AB, and we have put a short there, which is known as ISC. And now we are going to try to find the value of this ISC from the given parameters. Okay, so this is node X. We need to, and this is ground. I have not indicated ground here, but I should have been represented one ground here. So this is ground. Okay, zero potential out here. So now if you see the current coming into the node, we got to equate all the currents which is coming into the node X. Algebraic sum, we are going to equate it to 0. We are seeing Vx, so we are taking the current which is going out of the node to be positive. Okay, so that convention we need to remember. So Vx minus 50, because there is an 50 volt here. Across 20 ohms, if you see, on the left hand side you have 50 volts, and the right hand side we have Vx. So the current which will flow out will be Vx minus 50 divided by 20. And for this 60 ohm, this is going to be ground here. So the current which is going to flow out of the node through the 60 ohms will be Vx divided by 60. And here it is shorted out here, right? So this is again, so this ground will be available here. This will also be at a ground potential. So the current which will be flowing out of this node through this 40 ohm resistor will also be Vx divided by 40. And if you just simplify that, you get the value of Vx. Okay, now we are going to write the node equation at node A, right? Okay, now if you see here at node A, 10 amperes is coming into the circuit, right? And also this is Vx. So Vx, this is ground potential. Okay, since we have put a short circuit, so when we short these two circuits, the potential between these two will become the same. So this ground potential is available here also. So this current which is coming into this node at node A through 40 ohm resistors will be Vx divided by 40. So that is equal to short circuit. Now we have taken this convention sign to be coming down from A to B, so that is why that is equal to Is. Now if you substitute the value of Vx, which we found out earlier, we get the value of the ISC. Okay, so that becomes a simple way of finding out the Norton current source. Now we also, the next step is to find the Thevenin resistance. Okay, in this example, if you see, this is this is short circuit out here. So we have to find, so we need to remove this and see the input voltage input resistance as seen into the port AB. So you have 50 ohms which will get shorted, and this 10 amperes current source which will be open, right? That is the rule we have learnt earlier also. So to remove the sources, all voltage sources will be shorted and current sources will be kept open. So that will go open. So you have 20 and 60 coming in parallel. That is going to come in series with 40. That is going to be this is going to 20 and 60 in parallel. I think it will come to 15 ohms, and in series with 40, 55. So we put 55 here, and this is the load resistor. Here, which is there in the problem statement here, 50, right? So this is 50. Now this current we have computed here to be 10.618. Now what is the current going to this 50? That is the current division rule which we have studied in our theory. 10.7 into 55, that is the resistance which is coming in parallel, divided by 50 plus 55. Right, because there are two resistance. Higher the value of this resistance, lesser the current will flow into more current will flow into here, right? Because this is going to oppose the current flow. And so higher the value of the resistance which is coming in parallel, more current will flow here. So that comes in the numerator. You can remember it that way. So 10. This is the total current into 55 divided by 50 plus 55. So you get the current which is flowing into the 50 ohms. Is it clear to all of you how to solve these kind of problems? You have this is the Norton equivalent. Okay, so let's take one more example. Here we have an dependent source. Okay, so how to find out the Norton equivalent of this circuit? So the first step, like this is the 8 ohms, so we are going to short it. So we are going to write it as I short circuit and try to find out what is the current which is flowing this. So from here to here we have done nothing. We have just removed the load resistance and put a short circuit there. So this is a short circuit out here. So let's try and write the current equations at this node and this node, and then try to compute the value of ISC. So if this node, if I say now in this case the current which is going out will be 3 minus, okay, this is the current which is going out, so that we are going to take it as positive. So it will be minus 3 minus V1 by 2. Okay, so this is this 2 is denominator common for both these terms. Okay, it's appearing as if it's only for V1 by 2, it is common. So that is equal to this current, that is V1 by 6 plus since it's shorted here and is ground here, so it is ground potential available here, so it will be V1 by 1. So with this equation we get V1 is equal to 0.9. Okay, again we write an current equation at this node. So if you see, this is the short circuit current which is flowing here. Okay, this is one more current and which is 1 by V1 by 4, so V1 by 4, and the next current is this is ground potential here, so V1 by 1 ohm. Okay, this is the 1 ohm resistance. So using this equation we can find out, and V1 is already known as 0.9, so I can find out the short circuit current. Okay, now the next step is to find out the Norton resistance or Thevenin resistance, which is all the same. So instead of finding out the Norton resistance in certain circuits, it might be simpler to find out the open circuit voltage also, or the Thevenin voltage. So we will try and find out the Thevenin voltage here. So we have removed these nodes here, and we have represented this as VOC out here, right? So VOC, and then again we use the KCL at node 1. So V1 minus VOC, so this is the output voltage, we have taken it as open circuit voltage out here. VOC by 1 plus V1 by 6, okay, that is the current which is flowing into the 6 ohm, is equal to again this current into the 2 ohms resistor, which is 3 minus V1 by 2. Similarly, we are writing a current equation at this node. So that is again V1 minus VOC, open circuit voltage out here, what is available here, is equal to this current. Okay, that is, this current is 1 by 4. V1 has become now VOC here in this case. So no, sorry, V1 is this voltage, right? So it remains V1. So we equate this is the next equation. So by solving these two simultaneous equations, we get the value of VOC. Now RTH is found out by writing VOC divided by ISC. Okay, ISC we found out in the previous calculation, and here we are finding out VOC and then VOC divided by IC. This is nothing but the Thevenin voltage. Okay, and then we are dividing it with by ISC and getting RTH. Is it okay? So we can also find out RTH. Okay, also in this case, because there is a dependent source here, we need to apply VTH and then compute the currents and divide it by doing that, right? So instead of that, we are finding out the Thevenin voltage out here, okay, and then dividing it by ISC. So this is a simpler approach. Okay, is it understood, Sarvesh? Have you followed it?
Yes, sir.
Okay, so you can follow. Not necessarily every time you need to find out an RTH by the standard rule. If you are going to get a solution in a easier method by trying to find out VOC, you can always do that. And since we have seen this the relation between VTH and RTH, so even if you find out VTH, then RTH can be found out by using by VTH divided by IN. So this formula we can use to find out an RTH. Okay, so that was another example of it. Okay, again whenever we say about Norton's theorem, we need to understand what is the limitations. If I see, when I have defined the this thing, where is it? Okay, I have highlighted this aspect linear. Okay, linear means all the elements in this circuit has to be either a resistance, capacitance, inductors or transformers. You cannot have non-linear elements like diode, BJTs. Okay, then Norton's theorem you can't apply there. Okay, so that is the limitation which I mentioned here. Again, I wanted to just highlight this aspect again, so that it remains in your memory. So this circuit, if the circuit consists non-linear elements, then this theorem is not applicable. So you need to remember this aspect. Okay. Now the next theorem, again this is a pretty important theorem for practical applications, which is known as maximum power transfer theorem. Like in real life situations, they could be energy could be transferring from one module to other, several, it might be be moving from one module to several modules before it finally reaches the load. Okay, for example, if you have a solar panel, okay, it generates some currents based on the energy which is absorbed from the sun, and then you will have a controller, and then a battery bank will get charged, but that is DC obviously, so you will need an inverter, and then you will have a distribution system. So you see energy is being transferred from one module to other. Okay, there are several modules which come here. Similarly, you could have a windmill, or you could have an commercial power supply coming to your home, and both are generating some kind of electricity. So in all these things, what is important is we should know what are the conditions wherein maximum power is transferred from one mod as we move from one module to other. Okay, you just can't there has to be some kind of matching of impedances between the source which is giving the power and the next stage. Okay, now the source for this battery is the controller, and this is the load, and from battery to inverter, the battery is the source, this is the load, and finally this will be the load and inverter will be the source. So at each stage you will see that the energy is being transferred, and the role of the source and load keeps changing. So similarly, suppose you have a mobile phone or any communication receiver, you will have an antenna which will pick up RF signal which is available in the atmosphere. Some transmitter is transmitting, so a limited amount of that energy will be captured by the antenna, right? So that energy which is captured by the antenna needs to be transferred into your amplifier stage, and finally into your headset or whatever, if it would be a computer, whatever. So there has to be, if you see, there are several stages here. Here also the energy needs to be, the RF energy which is picked up by the antenna needs to be transferred into the RF front end. So there is a requirement of maximum energy transfer. Okay, so we'll see what are those conditions. Similarly, you could have an amplifier, and you could have speakers, and the impedance of the speakers could be anything, right? It could be an 8 ohms in a speaker, or a 4 ohm speaker, or there could be several speakers connected in parallel. So in all those conditions, whatever energy is being generated in the amplifier, that needs to be matched with that of the impedance of the speakers for maximum energy to be transferred into the speakers, which will finally emit out sound energy. So you will see in all these situations there is a need to couple the energy from one stage to other in a very efficient manner. So there are certain prerequisites for it. So we'll study that how it is done. Okay. Now the maximum power transfer theorem says that the maximum power is transferred to the load from a network when the load resistance equals to the Thevenin resistance. That is, there is a complex circuit. We have represented it as Vs and Rs here, Thevenin circuit. Now it says the maximum power that will be available from the source to the load resistance, that will be when Rs is equal to RL. Now if you see this plot here, this is the power which is available at the load. Okay, that is V square by RL, right? That will be the power. And this is the load resistance. So when RL is slowly increasing and then it has reached a value of RTH, that is the time maximum power will be available here. That means the maximum value of V square by RL will be at this point when RL is equal to RTH. And what is very pertinent to note out here is at that point it will be 50% efficiency. That means if say this source is generating 100 watt of power, 50 watts will be dissipated here and 50 watts will be available here. Okay, so there is no way you can, if this is generating 100 watt, there is no way you can take more than 50 watts in the RL, okay, as long as there is an RS in series. Okay, if there is no RS in series, then we'll see that aspect later on. So as long as there is an RS in series, only 50% of the power can be delivered into RL, and for that condition to happen, we should have RL is equal to RS. Okay, so that is the condition for maximum power transfer. So let's derive that equation and that condition. So this is VTH, this is RTH, and this is RL. This is a variable. As of now we are taking it as an variable. So the current which is going to flow into RL will be I is equal to VTH divided by RTH plus RL. So this is fixed, RTH is fixed and VTH is fixed. Okay, only RL is a variable. So I will be, it is just a simple mesh out here with one voltage source and two resistances series. So RTH plus RL. So the power is I square R, right? This is a standard equation for power. So I am going to replace this I from VTH divided by RTH plus here. So this is the substitution for I square into RL. And so I just expand it, and so this is the expanded form of the power. Now to find out what is the point at which what is the value of RL for which I get the maximum power, I am going to differentiate this power with respect to RL, right? Because RL is a variable out here. So when I differentiate here, RL is a variable, RTH and V is fixed. Okay, they are not variable, so they need to be considered as constant. So you just differentiate it, and then we know this, we have learnt it from our mathematics class. To find out the maximum point and minimum point, we generally equate it to 0. So we put it 0, so we get this value of RTL is equal to RTH. Okay, so this is the simple derivation to prove that when RL is equal to RTH, that is the instance where we get the maximum power from the source. Okay, and also we can substitute that value, this P max. Okay, that is I square RL, right? Whereas the power that is also written, can be written as VTH square by 4 RTH, or I can just write I square RL. And what is the power which is taken from the source will be I square RL plus RTH. That will become 2 into I square RL. Okay, the power in the load resistance will be I square RL, whereas the power taken from the source will be 2 into I square RL, because the power from the source will be RL plus RTH into IL square, right? So if you see, the efficiency comes out to be only 50%. Okay, so that we need to remember. So we'll take probably one problem and then try to understand this concept slightly better. Okay, so you have an 360 volt here, 30 and 50. So what should be the value of RL so that maximum power is transferred? Anybody? Ganeshwar? Can you make a guess?
150, sir.
No. See, we said it has to be Thevenin equivalent. Correct?
Sorry, sir. 4500 by 180.
Pardon? Yeah. 4500 divided by 180. Okay, you got to take a Thevenin resistance will be parallel of these three. Okay, so whenever there is a circuit given, don't jump to the conclusion it will be 30 or 150. Just be careful in your exams. You have to find out the RTH value. Okay, so in this case, to find out the RTH, we need to short this. So 30 and 150 will come in parallel, right? So VTH also VTH is again you can find out VTH also. So RTH is going to come as 25. So RL will be 25, right? That is parallel of 30 and 150. That is 25. So that is the value for which maximum power will be transferred out here. Okay. So this is about max. So you can have in the tutorials I include a few more problems on this, so that things will be clear. Otherwise it is a pretty simple concept. Okay. So before I end today's class, let me just give you some exemptions. This is an antenna. Okay. Most of the RF antennas are of 50 ohms impedance. Okay. So I'm just giving you some practical applications of this. So most of the antennas will be of 50 ohms. So whenever we design an LNA, that is LNA means low noise amplifier. That is the first amplifier which couples the antenna to our receiving station. It could be mobile. Mobile also will have a small patch antenna. Here a big antenna is shown just for pictorial representation. So most of the antennas will be 50 ohms. So the input impedance of all these amplifiers has to be matching with that of the antenna impedance. Okay, so most of the antennas are 50 ohms. So the input amplifier impedance also will be 50, so that maximum power, RF power, which is available will be coupled to the input stage. Similarly, when I am transmitting, so these antennas have to be are all 50 ohms, because the same antenna will be used for receiving as well as transmission. So in that case also the output amplifier will have an output resistance of 50 ohms. Otherwise what will happen, whatever you are trying to transfer, say if you want to transmit say 100 watts, if the impedance is not matching, so the output power which will be radiated will be less than 50 watts, and rest of the power will get dissipated within the circuit and it will generate heat, right? So so you have to be careful. So you understand it's all very critical. In the receiver section, if you don't match it properly, you might not get the entire energy. Okay. Whereas in the transmitting section, if you don't do the impedance matching properly, the entire energy which you want to transmit will not get transmitted, and instead they will get dissipated as heat in the circuit. So that is the so always impedance matching is a very, very critical issue. Okay. I'm not wanting to confuse you with this, but let me just cover this aspect also. If you see an op amp, okay, and the op amp has got R out almost equal to 0. Okay, that means it will have an volt. If you make an amplifier using an op amp, okay, the output voltage will not have a series resistance. Okay, Thevenin resistance, which will approach almost 0. So if you see the power equation is I square into RL. Okay, this is VTH, RTH plus RL. This RTH is almost 0, right? So you can see that in this particular case, if you keep decreasing the resistance, okay, the power will keep increasing, because it is V square divided by RL. So there is where RTH is almost 0. Okay. So what we are doing is, there we will see only this portion of the curve, because RTH is almost 0 in that case. Okay. So there is a possibility of it is not that you will get this curve always. This is for a finite RTH. Okay. If RTH is 0, then the curve changes. Okay, it will keep increasing as you keep decreasing the RL. Okay, not increasing RL, with decreasing RL, because power is V square by RL, right? So this will be this left hand side portion of the RH is going to get merged with this dotted line is going to get merged with the y-axis. So as you keep increasing RL, the power will decrease, because it is V square by RL. Okay, so that is one exemption to that rule. So just for academic interest, I have just for a practical point of view I have put that, but otherwise we restrict for our exams sake with this kind of graphs. Okay, so that's all for today. If you have any doubts, you can ask me now.
Thank you, sir.
Okay, thanks a lot.